Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
Hey, David.
Hi, Yannick. Last episode.
Yeah, the conclusion. The end of the road.
It's all going to make sense now.
Indeed, indeed. Speaking of making sense, actually, I was thinking like this episode we can focus on learning, what our agents have learned and what we've learned.
Oh, nice symmetry.
Indeed. One thing we talked a bit about in the previous episode is whether we could get a bit of a sense of what we think the agents may have learned and any patterns in how they play the game. And that's what I wanted to talk about. I went and I collected some stats from our agents and have a few notes to share.
Okay.
So I mainly looked at three different things, or sort of three things I could extract. And one was, where do they make their first move? So whether that's either they're going first or going second. When do they play a double move? Because they only have one double move to play in a game. Do they do that early or do they do that late? And sort of when they play a double move, where does it go? Where do they choose to put those two marks? So for your agent, where does it put its first move? So when it's going first, your agent always plays in the center, right in the center of the board.
Okay. How about second?
Before I do that, I should explain one thing about why it always plays in the center. One reason is that the way your agent is set up is that it will always do the same thing given the same board state. It's always going to pick the highest probability move that the model gives it and play right there.
Also known as the best move that it knows
the
of,
best
right?
move.
So, okay.
Yeah.
It wants to do that. Makes sense.
Yeah. So given an empty board state, it believes the best move is to play to the center. It's kind of cool.
Oh, yeah, which, I mean, this is the sort of thing I think you shouldn't do with machine learning, but it's just tic-tac-toe or tic-tac-toe. It seems to accord with, let's say, the human intuition that center square is the most valuable one, and which is not just an intuition, it's the one that's in the most winning rows.
That's true, yeah. It's in some ways what we'd expect or what we'd hope to see, some bias towards picking the center.
And as you say, because my model always looks for the most probable for any board, always the same thing, always in the center. Way to go. I like to think that if it were to mix it up, it would play the corners. But, it's always playing the best move it knows.
I can tell you a little bit about that from the second move. So when it's going second, my agent's already played a move. And this is what it does. So it mainly puts it in the top left about 50% of the time. So
again, that accords with human intuition, at least for tic-tac-toe. Although it's a little weird that it's not noticing those other two corners.
Maybe, but
maybe not.
They're no worse than the corners it picked, so there may be no need to pick that. And again, it's just picking the best move it thinks given what I've done or what my agent has done. So, yeah. So its first moves are pretty much matching the kind of thing you'd hope it learned.
Yep.
Next, I want to talk about when it plays double moves. So I will say yours did play fewer doubles than mine. Overall, in 500 games, it played only 42 doubles.
What?
Yeah.
No.
Yep.
Huh. Well, that's basically a bug.
Maybe.
Well, no. I mean, in my data.
Well, remember we talked about your doubles being much rarer, so that could be part of why it doesn't play those as often.
Yes, but my unit tester went through, and like 80% of the games, it plays two doubles.
Okay. Well, your agent didn't.
Okay.
And in terms of when it plays it, it typically plays it a bit later in the game. So the earliest it played it was turn 9, and it mainly plays around turn 12 and 14. That's when it puts down a double move.
Will it bother you if I try to act as if I have some understanding of what it should be doing? Because I'm about to. So, as you know, when I'm generating the games, for every move, if the player still has a double to play, it rolls a 8-sided die, it spins the dial, and if it comes up, if the number is 1, that's totally arbitrary, then it plays a double. So it should be playing more doubles in the first 8 of its turns than the data seems to show that it's doing.
Yeah. So I think it's good to remember that while you did generate some data your agent has to take all of those things and sort of generalize it against all the patterns you're trying to teach it. And this is what it ended up learning. So in some ways, you would expect it to be in some ways different from the data you generated because that was sort of random and you want it to do a bit better than random. But yeah, there won't always be necessarily this one-to-one match of like, oh, here's the distribution I expect here, especially when there's sort of different kinds of moves like we have here. So maybe one way to look at this, like this is the summary of when it tries to compress all the information about all those kinds of moves together. It may lose some information about when to play doubles well. That would be something to look at. I was like, okay, how can I improve its ability to use the double move?
Okay. My temptation is always to try to over-understand what the machine learning system is doing. So
yeah. The other thing I want to talk about was what kinds of double moves does it play when it makes them? So we already recognized in a previous episode that because of a limitation in our labeling coding, that your agent cannot play a double with both marks in the same square. So I just wanted to see if there was any patterns in the doubles it did make. And I couldn't really discern any strong patterns. There wasn't like one or two that were much more common than the others. No particular move was over 12% of the doubles in total. Looking at the marks, I did notice it did not play corners very much. However, given that these were often later in the game, I suspect that maybe the corners might have been taken. So I'm not 100% sure of that, but like given knowing that it plays a bit later, it's possible that the corners are already occupied, and that's why it can't really take corners.
There could have been patterns that we wouldn't obviously notice, perhaps, because tic-tac-toe boards and tic-tac-toe boards are symmetrical in multiple directions. And so two sets of moves that may not look the same may, in some mirror world reflection, diagonal symmetry might be the same, or something like that, or something more complex than that.
I do think there are patterns that we can't see from this analysis. There's a lot of like interaction between agents that we're not really looking at it very closely. In terms of stuff like that, mirrors, we should be able to see that or examine that from looking at where the marks go.
In any case, it's not like my model always playing the center on its first move. It's at least more complex than that.
Exactly. When it came to doubles, there was basically no pattern I could say. For my agent, I have a similar set of analyses. And I should say one difference in my agent is that it doesn't always play the highest probability move given by the model, what you call the best move. It doesn't always play that. It will choose, I think, essentially from like the top 5 according to that probability distribution.
Choose randomly from those top 5.
Not randomly, but according to the probability. So the most likely one will get picked more of the time, and less likely ones will get picked less of the time, according to those actual probabilities.
And why on earth, if you are ruthlessly set on crushing your opponent, and maybe I'm just speaking for myself here, why would you take that strategy?
Mostly because I'm not ruthlessly set on crushing my opponent. And in this case, it just honestly made for something that's more interesting. If both of our agents play the best move, then you essentially get 2 games. One where yours starts and one where mine starts. And they always do the same thing. They get sort of stuck in a pattern of the same behavior. So I thought it would just be more interesting to allow it some variety.
Yeah, someday we should have your mediocre choices of your model play my model's mediocre choices because, maybe I'm a better mediocre player. Maybe that's the problem.
Maybe in that mid-range.
I am so desperate to grab whatever honor I can.
And I should say, it most often will pick the highest probability move because it's the highest probability move. It just allows some flexibility there. So with that, going first, its first move, if it's going to play first, 25% of the time, it immediately plays a double in the center position. So it will immediately try and capture the center, which is kind of interesting.
Yeah, it's very interesting. And I don't mean to harp on this, but you can capture, because of the vagaries of how moves were encoded, your model can play doubles.
Yeah.
In the same square.
In the same square.
So you can just first move, boom, take that center square and own it. I can drop one of my marks in the center square, but I need to get 2 in to own it. So in every case, if you want it, you can have it.
Yeah. And in this case, 25% of the time when it goes first, it will try and do this. I also noticed that this is the only double move it makes where it puts both marks in the same cell.
Really?
Yeah. All of its other doubles are spread across different cells. This is the only one. And yeah,
Yeah.
that's just what it did. And it worked well enough for it that it was fine. Then after that, there's 4 moves that are each as likely. They're just under 15% of the time and include a single move that's played in the lower right corner and some other doubles that the marks are spread around the corners. There's also one that just does it in sort of the middle right that isn't a corner. That's as likely as the other. So occasionally it doesn't pick a corner, but that's what it does when it goes first. Like you're asking when it goes second, this I found kind of interesting because the probability of playing a double in the center went up a bit. It went from 25% to around 35%.
Ah, it sensed the danger I was posing to your entire house of cards here, and it.
Yeah.
Huh.
And it didn't always respond in that way, but just 35% of the time, because you play it always in the center, mine will respond by trying to take that center back. Else it does the same thing as before. It just sort of tends to play a double with marks spread around the corners.
Yeah, well, that sounds like reasonable advice, I guess.
Yeah. In terms of when it played a double, it played it much earlier in the game. So one, I should say, mine played about 450 doubles out of 500 games. And it tends to play within its first 3 turns. So it goes pretty early.
Yeah, again, I don't mean to make sense of these things, but it seems to make sense to play early rather than later, especially if you're, well, in my case, I'm training on random moves. It's very hard for my model to know when the game's going to be over.
Yeah, it doesn't really have that time aspect.
That's why I set the odds to 1 in 8, but it seems not to have, for whatever reason, picked that up. Interesting.
Yeah. So that's basically, a little bit of insight into what they're doing and maybe a few strategies that they picked up. So more than just sort of playing the rules legally, this is maybe a little bit of strategy they've learned.
So there's clearly a ton more analysis that could be done. It might not show anything, but analysis that might uncover interesting patterns or exceptions or whatever.
Yeah, exactly. Or causes for why it does certain things in certain situations. Yeah.
What exactly triggers yours to play a double? Might have some pattern that could be understandable. And
like in the time when it plays second, is it really responding to the fact that you played, or is it kind of coincidence? That kind of thing would require further analysis and more digging into.
So if this were an actual important application, we might be well motivated to do some more of that analysis, including using tools that have been developed to look more closely to much larger volumes of data.
Yeah. And this, briefly touched on the sort of subfield of machine learning interpretability and how can we interpret why the model does some of the things it does, as well as we might want to produce more kinds of test data that check certain conditions and check that it behaves the way we want, which is not interpreting why it does that, but at least it helps us characterize the kinds of things it does more precisely. So we'd want to look at that more precisely than just sort of picking a few features to look at. But yeah, we definitely look in that more in depth.
Yeah. For example, I'm tempted to go back now because, as I say, in the vast majority of games, doubles are played for generating data. But in the outcome, in the actual play, only 10% of the times, which is really surprising to me. So I would like to go back and see whether I actually screwed up the data again and it actually recorded fewer than I thought. Pretty sure I didn't, because I do check for that, but that would be one type of forensics, simple forensics we could do, I guess, too.
Yeah. So that's kind of it for what the models have learned. I'm curious for us to discuss what we've learned in this process and what have you learned, David?
I suspect that I learned more than you just because of our starting points. So first of all, I've learned what the sort of big chunks are of the highly simplified sort of machine learning application. It's a real one, but on purpose, we kept everything simple enough to be able to do over the course of these weeks and to be able to talk about it. So I think the steps along the way are much clearer to me. Another thing that's become clearer to me, machine learning is a type of application. It's an app. That's what you end up with. And we are used to thinking about apps as sort of these self-contained things, and the programmers program them and they work, and that's that. And you do end up with that with machine learning. You end up with a model and a way of asking the model questions, and you put it up on a nice web page or whatever it is that you're doing. And so, yeah, it's an app in that sense. But in trying to understand it and to see how it's coming up with what it does, insofar as we can, it's not enough to think about it as just an app that's been delivered to you, because it is so dependent upon, for example, the data. Very difficult issues around deciding what the data you're going to use is. It's going to train itself on the data, right? So that's going to be really crucial. There's a lot of human decision-making in that, which we're going to talk about very soon, I hope. And then you also have to do things like decide what output you want, and also how confident you want the system to be when it makes a recommendation, when it plays a move, because maybe you want it to recommend 5 moves, tell you what the probabilities are, and you get to choose. I mean, it's not simply a little wind-up machine the way a normal computer app is, where you put in an input and out it comes. I mean, that happens, but the process of building it is integral to understanding what it is, how it's not working, how it is working, and the rest.
Yeah, well put, well put.
Which brings us to the next thing, which is just how important the data is.
Yeah, the data is super key, and in many places ends up being that main thing you want to go back and look at and debug and change in order to affect the system.
There are also obviously questions about how much data you need. More is not always better. As in fact, I've found out, I may have been doing this in a buggy way, but at one point training it longer on more moves actually drove down performance in the actual game player. And then questions, and we also have spent a lot of time on this, how to encode the data, how to bring it into the machine, what sort of data it needs to see, and how to express that. And how to express it often is a pretty technical issue, but just figuring out what data it needs to learn from and how to tell it that data is not trivial, even for tic-tac-toe, where it's as trivial as it can be.
Yeah, and that question of sort of transforming it and figuring out how to pose sort of the question or the learning problem to the system is a key step and is a part of getting it to a place where it can learn something effective. And while you say it is somewhat technical and mathematical, that is another important lever where you, given a certain kind of data, different strategies in order to make learning most effective from that data, and ends up being super important. And that's where you have a large proliferation of different machine learning algorithms and techniques and tricks and things that are used to extract useful knowledge out of the data set.
Very, very early on, before we actually started, I asked about whether we could train a system to play tic-tac-toe, not by giving it more or less a numerical representation of the board. You know, it's 9 numbers representing the state of each of the squares, but instead basically took a picture of each board and use a different type of algorithm, I assume, to try to get it to decide what the next board should look like.
Yeah.
I don't know. It certainly seems more complicated than the way that we did it, but that's a choice too.
Yeah, that's a choice. And depending on how you can get the input data, that would have involved more technical resources, but actually would have been a very similarly structured problem and similar algorithm. But the model type would have been different. You would have gone for something that is better at understanding images, and things like training time and other things would have been definitely increased and would have required a bit more maybe expertise and delicacy in like just handling that data, because there's just a lot more data points, so to speak, when you're just going from an image than our nice representation of here are the actual marks. If you just give it an image, it would have to learn, how do I interpret this image before it even learns how do I play tic-tac-toe. So it would have scaled the problem complexity a bit higher. Conceptually, a lot of things would have been similar.
Yes, it would have gone from a board, you could express a board in 9 numbers, 9 characters, the way that we did it, or if it were an image, every pixel. It's a lot more than 9 pixels. And so, okay.
Yep.
I'm not saying it's a good idea.
Definitely doable.
One of the huge confirmations for me was, being brought to face with the fact that even though machine learning is a type of artificial intelligence, and artificial intelligence has the word intelligence in its name, machine learning doesn't, and you can't hear my podcast air quotes, doesn't think like us. It doesn't think at all. Whatever temptation I might have had to wonder if machine learning, at least at this level, is any form of consciousness. And I will tell you, frankly, I'd never had that inclination, but many people do. I have none at all at this point. And if it did, its way of thinking about things is so, so different from ours. And we talked about this when talking about how to represent a board, because we think of a board, tic-tac-toe board, as a grid, 3 by 3. And for that reason, we can see with our eyes why a winning move is winning, because we can see the rows and the diagonals that it's making, 3 in a row. But if it's just 9 characters, most of the winning configurations of that are not. You don't have 3 consecutive X's or 3 consecutive O's. If it's 9 characters and you won by going from left top to bottom right diagonally, that doesn't look like anything significant to a human.
I think I found this discussion interesting in the past because to me, it's an open question as to like what's the internal representation of the model. Yes, the thing we give it at input time is that string, but is the internal representation closer to something that gives you the semantics of a grid or not? I don't know. And I think it's interesting to wonder, but I can see where you're coming from. It is definitely a very different representation. And there's sort of maybe different affordances in how we think of our thinking, because I think that's the thing we have access to, the thinking about our thinking. I'd say relatively few of us that maybe know how the thinking works, but it is different from the representations we think about versus the representations we give to the agent.
Yannick, I have a question for you. I mean, we've been iterating for weeks on what are essentially projects so small that reasonable people wouldn't use machine learning for them. Tic-tac-toe, maybe. When you scale up to an actual or even large machine learning project, what's different?
Yeah, I definitely wanted to talk a bit about this. If this were maybe more of a quote unquote real, though this is a very real project, I think one initial thing that we would do when we're just thinking of the problem is stepping back and asking ourselves, is machine learning the right solution? Is it worth the time? Does it give us the control we need? Is it the right approach to solving the problem? I would say, in this case, even for Tic-Tac-Toe, I'm pretty certain the answer would be no. Like, if we were really bent on building the best player we could, I doubt we'd start with machine learning first. As a learning exercise, I think it's totally fine. I actually think it's good to do things that are a bit simpler than you would otherwise target so you can understand them a bit better. But it's important to think about these things, particularly as you go into like higher stakes situations, whether the machine learning solution is the right solution. We've talked about some of the challenges of sometimes understanding what it's doing. So I think that's a first important question in a project. Another thing, and maybe this will give some people some comfort, is while it was fun implementing a bunch of stuff from scratch, in a bigger scale project, because we weren't inventing new algorithms, we probably would have used existing sort of higher level coding abstractions that are like more battle tested and, have been reviewed and sort of have fewer bugs. It was useful to sort of go into some of the details to get that very hands-on approach. But given we weren't inventing a new algorithm, there's enough scaffolding out there that would have probably used some abstractions. And even if not, even if we were writing something from scratch, I'd say one other difference is doing something like this benefits from collaboration and code review from other humans. So we made all of our human decisions kind of on our own. I made a bunch for me, you made a bunch for you. We talked about some of them. But in many situations, getting perspective from more people is really helpful in enabling machine learning systems to encode the right things. So in a larger scale thing, that collaboration, maybe discussion about some of those choices and what they might lead to is a helpful part of it.
Crucial for me, in fact, you are overstating the balance and symmetry of this relationship. I mean, I literally couldn't have done it, but it's good to know that you who could do it benefited from discussions with collaborators, by which I mean not just me.
And the higher stakes it is, the more you want some of that for sure. I think another thing that would be different is finding more rigorous ways to document our experiments and findings as we tuned various knobs. Like, it was fun to experiment. We did some in a sort of more real project. There's a bit more rigor in that part and how you capture things. And for me, this also relates to maybe one challenge in machine learning projects. Like, there's a lot of things you could change. So sometimes it's important to find a small subset of the things you want to focus on at that moment, and then sort of systematically work through those and then go back and find maybe a different subset. But that's one thing we would have probably done in a larger project. And lastly, one point I wanted to make that we sort of alluded to is we probably would have thought a bit more about guardrails that we would want to put around the model to make sure it doesn't do something we don't want. And I'll give an example or analogy. In this case, we had our model and we had our agent. And even when the model outputs an illegal move, we let the agent play it. Whereas it's a relatively simple check to be like, if this move is illegal, don't play it. Like, don't do that thing. And that kind of coding, those kinds of guardrails, we would have put more effort into thinking through what are the maybe hard guardrails we want to put around what comes out of the model. Since, you know, there are all of these probabilities and things, we probably wouldn't, in a higher stake situation, allow the sort of equivalent of disqualification if we can easily detect it.
Since what we're getting back from the model, both of us, when we give it a board and ask what move, is a set of 9 possibilities, each of which has its own numeric ranking. And I'm always taking the highest ranked one, and you allowed more play. If my model had delivered an illegal move, the system could go back and say, okay, give me your second best, and hope that that one plays. Okay.
Exactly. Yeah. Or sometimes stop. Sometimes the right thing for an algorithm to do is stop and not apply an action if that's safe to do. So yeah, exactly that kind of thing. And, you know, probably, again, in a larger scale project, we would have gone back to some of those choices we made around model architecture that are maybe more well adapted to the problem. Here we did, at least from my perspective, I tried to choose relatively simple model architectures and approaches and techniques that we could use, but it can get a bit more technically complex.
I would hope and assume that in a larger model, especially one of some significance, that part of the, so to speak, guardrails, part of the process, and part of the human decisions would involve people who are not just the developers, but also the client who is asking for it and what that person wants. And if there are any possibilities of ethical concerns, that there be ethical reviews and community involvement and reviews before it goes live and testing before it goes live and monitoring, so to speak, afterwards to make sure that it's performing as it should. It's not having unintended consequences and the rest of it. And so the human element gets larger and larger, I hope and assume, for machine learning systems of consequence.
Yeah, as the stakes get higher, you have more of that desire for accountability around it.
The fact that my model played illegal moves 1% of the time means nothing. It would matter if it was a machine learning system being used for something where lives are at stake, for example. That 1% would not be acceptable.
Exactly. Yeah. So those are some differences, and there's more, but those are just a few things I wanted to highlight for listeners.
That brings me to what for me is the thing that I think was the most important thing that I learned and really learned experientially, which is the extent to which these systems, which are sometimes, some of them are called black box systems because we're not sure how they're working, that even black box systems are very human systems in that they are created by a pretty vast set of human decisions. In the case of just figuring out what data to use, how to use it, which algorithms to use, what sort of, all of that, those are human decisions. But so are deciding, as you made really helpfully clear to me, is decisions about, well, when is the system trained enough? When is it accurate enough in its training that we think it's okay to use? And it's one thing for tic-tac-toe, it's another thing for book recommendations, and it's another thing for a college application, machine learning sorter or whatever. Also in terms of, is this a system where we can tolerate more false positives or more false negatives? And that turns out to be a crucial set of distinctions, which we have to decide upon in each application. We humans have to. Also, with games, with tic-tac-toe, it's really easy to say what constitutes success. So your model marginally outperformed mine. It just squeaked by in beating me. Mine beat yours a full 18% of the time, so which rounds up quite nicely to 20%. So in a game, it's easy to say success means winning the game. In other applications, it can be much, much, much harder. And a lot of what's being written and spoken about and concerns about machine learning have to do with trying to figure out what success means for a particular application. Usually easy for a game, but if it's a system that's being used to evaluate teachers, what constitutes a good teacher? Kathy O'Neill uses this example in her book, Weapons of Math Destruction. As a society, we don't have a single opinion about what constitutes a good teacher. There are lots of different ideas about what that means and how to measure it. And if you're going to program a machine learning system, train a machine learning system to evaluate teachers, which I'm going to say personally, probably not a great idea. But if that's what you're doing, you're going to have to decide what exactly constitutes success and how you capture that in data. Those are very big human decisions, among the largest, that surround this technology that it turns out is completely shot through with humans deciding this or that, that or this.
Yeah, it's been really interesting to see the interplay between human decisions and data and algorithms that sort of come together in the process of building something like that. And I think that's been illuminating for me. I hope it's been that way for you, or it sounds like it's been that way for you. And I hope that it's been that for our listeners. So with that, we're kind of coming to the end of this, and it's been a fun ride. We invite folks listening to visit our website, pair.withgoogle.com/thehardway, where you can see the agents play against each other. You can also see contact info for us in case you want to reach out or you love the show and want to tell us about it.
You can get the code there as well, although it would be a personal favor to me if you never, ever looked at my code. Thank you very much. The address again? What's that address?
pair.withgoogle.com/thehardway.
So, and with Google is obviously all one word.
Indeed.
We both have our Twitter handles up there. Mine is D. Weinberger. Yannick, thank you. I cannot tell you, A, how much I've learned, or B, how much fun it has been. I could tell you. It's been a lot. It's been wonderful for me. And you are an incredibly patient and helpful and clear and kind person. So thank you.
Thank you. I've learned a lot too. It was a fun exploration of a different side of machine learning for me. So it was a lot of fun. Well, thank you very much. And thanks for listening.
Thank you very much.
Bye. You've been listening to Tic-Tac-Toe the Hard Way with your hosts Yannick Asogba and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
and the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.